Most of the time we think of numbers as, well, fixed, right? A price is a price, a speed limit is a speed limit. But what happens when you need to calculate something, but a key value could change? How do you build a formula for that? Well, to do it, we need to unlock a kind of secret code in math.
Okay, so let's put ourselves in a real-world scenario. Imagine you're tasked with designing a brand new square park. You need to figure out how much fencing you'll need for the perimeter and how much grass seed you'll need for the total area. Here's the catch. The final side length isn't decided yet. It could be 10 meters, it could be 20, who knows? How on earth do you create a formula that just works, no matter what length they finally pick? To tackle this, math gives us a couple of fundamental tools. First up, you've got your constants. Think of these as solid as a rock. They're values that never, ever change, like the number 2 or 100. And then you have variables. These are the cool ones. They're like empty boxes, placeholders like x or y that can hold any value that might change, like, say, the side length of our park.
So, what happens when you start mixing these things together? When you take your constants and your variables and you combine them with operations like adding, subtracting, or multiplying, boom, you've just created what's called an algebraic expression. So for our park, if we let x be the side length, the expression for the fence is just 4 times x, or 4x. And for the grass, it's x times x, which we write as x squared. And just like that, we have formulas that work for any side length.
But here's where it gets interesting. Not just any old algebraic expression can be called a polynomial. Nope. You can think of polynomials as a kind of mathematical VIP club. And to get past the velvet rope, every single expression has to follow one very, very strict rule. And here it is, the one rule to rule them all. The power, the little exponent, of any variable in the expression has to be a whole number. We're talking 0, 1, 2, 3, and on. No fractions, no negative numbers. They're not on the list. This one simple rule is what gives polynomials their incredible properties, making their graphs these beautiful, smooth curves with no weird breaks or sharp turns.
So let's play bouncer at the club door for a second. An expression like x squared plus 3x plus 1. The powers are 2 and 1, both whole numbers. Yep, you're in. Welcome to the club. But what about 1 over x? Well, that's really just x to the power of -1. The power's negative, so nope, sorry, you're not getting in. And the square root of x? That's the same as x to the power of 1/2. It's a fraction, so denied.
All right, so now that we're inside the club and we know how to spot a polynomial, let's, break one down. Let's get to know the family. Let's put this one under the microscope. 5x squared minus 3x plus 7. First, you see the chunks separated by the plus or minus signs? Those are called terms, so we've got 3 of them here. Next, the number that's kind of hitching a ride with a variable in each term, that's the coefficient. So 5 is the coefficient of x squared, and notice for the -3x, the coefficient is actually -3. And finally, that number hanging out all by itself, the 7, that's our constant term. Now, in every polynomial family, there's a leader, a boss, and the power of that boss term is called the degree of the polynomial. It's really simple. It's just the highest power of the variable you can find anywhere in that expression. And the degree is incredibly important. It tells you pretty much everything about the polynomial's name and its behavior.
This degree is kind of like its last name. A polynomial with a degree of 1, something like 4x plus 2, gets the name linear. If that boss power is a 2, like our park's area formula, x squared, it's called a quadratic. And if the highest power is 3, it's a cubic. You are going to see these 3 all over the place. Okay, so we can spot them, we can name them. But what's the point? What can we actually do with them? It's time to go from theory to action. One of the most important things we can do is find the 0 of a polynomial. Now, this sounds a little weird, right? A 0 isn't the number 0 itself. It's a magic number. It's a special value that if you plug it in for x, the entire expression, the whole thing, equals 0. So for a super simple polynomial like x minus 1, the 0 is 1, right? Because 1 minus 1 is 0. And this is where things get really cool. Finding those zeros unlocks a super powerful tool called the factor theorem. And it's awesome. It basically says that if you find a number, we'll just call it a, and that number is a 0, then you automatically instantly know one of its factors. It's guaranteed to be x minus a. This is an absolute game changer for breaking down complicated polynomials into simple pieces. So, how in the world do you find a zero? Well, for quadratic polynomials, one of the most powerful and honestly kind of fun methods is a clever trick called splitting the middle term. Okay, let's get our hands dirty with this one. 6x squared plus 17x plus 5. Step 1, you multiply the very first and very last numbers. So 6 times 5 gives us 30. Now for the puzzle part. We need to find two numbers that multiply to get 30, but add up to that middle number, 17. Think about it. 15 and 2. That works. Now for the magic. We use those two numbers to literally split that middle term, 17x, into two pieces, 15x and 2x. Now we just group the first two terms together, group the last two terms together, and pull out whatever's common from each pair. Stick with me here. Watch what happens. And just like that, look what we have. We're left with our final answer. That whole complicated expression was really just two simpler pieces multiplied together, 2x plus 5 and 3x plus 1. We've basically broken the code and found its building blocks. Now, you might be thinking, this is great for my algebra homework, but what about real life? Well, polynomials aren't just for class. Some of their core rules, these things called algebraic identities, can give you what feels like a mathematical superpower. Get ready for your new favorite party trick. I want you to try this. Right now, in your head, no calculator. What's 105 times 106? It sounds kind of tough, right? But I promise you, a polynomial identity makes it shockingly simple. Here's the secret. You have to stop seeing it as 105 and 106. Instead, think of it as 100 plus 5 times 100 plus 6. Now, does that structure look a little familiar? It should, because this structure follows a reliable shortcut, an algebraic identity. The pattern tells us that the answer is always the first number squared, plus the sum of the other two numbers times that first number, plus the product of the other two. So for us, that's 100 squared, plus, well, 5 plus 6 is 11 times 100, plus 5 times 6, which is 30. And all of that is math you can do in your head. You've got 10,000 plus 1,100 plus 30. And what does that give us? Boom, 11,130. No calculator needed. Pretty cool, right? We have gone through a ton of stuff, from the absolute basics of what a polynomial is, all the way to a mental math party trick. So now, it's your turn. Let's put that new knowledge to the test. Here's challenge number 1. Take a close look at this expression, y squared plus the square root of 2. Is this a polynomial? Now, be careful. Think back to that one single strict rule for getting into the VIP club. Does this expression follow the rule? And for our final challenge today, what is the degree of 5x cubed plus 4x squared plus 7x? Remember, just find the boss term, check its power, and you'll have your answer. Because once you learn to read this language, you'll start seeing polynomials everywhere. They're the secret code behind everything from designing bridges to creating the graphics in your favorite video games.